Hello, welcome to lecture 4 of Elec Eng2CI5. We'll be discussing in this lecture Kirchhoff's laws, and these are two important laws that we're going to be using over and over again in this course. We use them to analyze circuits to determine the currents and voltages in different branches, and later we'll be basing on these. We'll be using these laws to develop and some analysis techniques like nodal analysis and loop analysis and so on. So these are very important laws, and we'll have some examples on that. Okay, Kirchhoff current law, we abbreviated as KCL. KCL states that the sum of currents entering a node is equal to 0. So a node is where a number of branches meet. So for example, if you have a circuit where you have a number of branches like this, so this would be one branch, this is a second branch, the third branch, maybe there is a current flowing here, current flowing this way, a current flowing that way. Okay, so we have three currents, and this node is where these branches meet. So the sum of all currents entering this node must be equal to 0. And this is one way of stating Kirchhoff's law, KCL. There are two other ways of stating it. The sum of currents leaving a node is equal to 0. And the sum of currents entering a node is equal to the sum of currents leaving a node. All three formulations are exactly equivalent. For example, if these currents, let's give them numbers. Let's say this is maybe 3 amperes, okay? This one is 2 amperes, and this one, let me just erase this one here. And this one, so this 2 amperes, this one is minus 5 amperes. Okay, why did I put this one as minus 5? Because it is flowing into the node. Okay, these two are flowing in, and their sum is equal to 5. But the sum of all currents flowing into the node must be 0, so this one must be minus 5. So the sum will be minus 5, 2 plus 3 will give you 0. Okay, I can treat them as well all as currents leaving the node. Okay, I'm taking the references as currents entering the node, but I can make this one minus 3 ampere and treat it as a current leaving the node. I can make this one minus 2 ampere and treat it as current leaving the node. So in that case, it will be 5 minus 2 minus 3. I give them all negative sign. Or I can redraw it in a little bit different way. I can draw it something like this here. So I can do it that way here. So I can simply say that this is 2, this is 3, okay, and this is 5. So we have here two currents flowing into the node and one current flowing out. So 5 must be equal to 2 plus 3. This current must be equal to the sum of these two currents. So there are three ways of writing KCL. They are all equivalent. The difference between the first one and the second one is simply a negative sign, while in the third one we move some terms to the other side. We say that 2 plus 5, I1 plus I2 is equal to I3. 2 plus 3 is equal to 5. So we divide them into currents flowing into the node and currents flowing out from the node. So this is a statement of KCL. It's a very simple statement, and the most important thing, when you apply it, you give every current the proper sign. Otherwise, you end up with the wrong answer in your question. Okay, we have here a circuit. This circuit has only one source, a current source here. Its value is 12 milliampere. We have a number of resistors, R1, R2, R3, R4, and R5. We have here actually in this circuit we have actually three nodes. This is node number 1. These three branches meet. This is node number 2, where 1, 2, and 3 branches meet. And this one here, this whole point, this is just one point here. They all have the same voltage. This is one big node, but we stretched it, okay? So in this node we have 1, 2, 3, 4 branches meet, okay? But usually, and as we'll explain later, not all the equations that we get at these nodes are independent. Only 2 here are independent. This is why I'm going to focus on node 1 and 2, and I'm going to ignore node 3. This will become clearer when we analyze circuits. So let's talk about node number 1. there is a current flowing in. We know it's flowing in. Its value is 12 milliampere. I don't know whether I1 and I4 are flowing in or flowing out. When I start to analyze the circuit, I may not be sure. So I'm going to give them a reference direction. I will assume that I1 maybe is flowing to the right, I4 is flowing to the left. And then I start to do my solution. If I get a positive answer for I1, then it's indeed flowing in this direction. If I get a negative answer, this means it's flowing in the opposite direction. Okay, the same thing applies for I4. So we give every current a reference. If you don't know its direction, you give it a reference direction, and then you solve using nodal analysis, mesh analysis, superposition, whatever the technique you're going to be using. I'll be talking a lot about these techniques. Then if your answer is positive, then your assumption of direction is correct. Otherwise, your assumption is wrong. So now we can apply KCL at node number 1. We can treat it first at sum of all nodes, all currents entering this node equal to 0. This is entering, so this is 12 milliampere. This is leaving, so it's going to be minus I1. This is leaving, not entering, so it's going to be minus I4. So 12 milliampere minus I1 minus I4 is equal to 0. This is the first statement, the sum of all currents entering the node equal to 0. So when a current is leaving the node, we put it with a negative sign. 12 milliampere minus I1 minus I4 is equal to 0. Now, let's talk about the second formulation. The sum of all currents leaving the node equal to 0. So this is leaving the node, then you have I1. This is leaving the node, you have I4. This is entering the node, then this becomes minus 12 milliampere. So the second formulation is I1 plus I4 minus 12 milliampere is equal to 0. This is what we have here. And if you take a look at this one and this one, the difference between them is a negative sign. And as you know, one equation, when you solve a system of equations, the system is not affected if you multiply one equation by a negative sign. So this really does not affect your solution of a circuit in any way. The third one, which is I find usually more easier to work with, say the current flowing in is equal to the current flowing out. So I have here only one current flowing in, so 12 milliampere must be equal to I4 plus I1. So this one here is exactly equivalent to this one or to this one. After we move maybe the 12 milliampere to the other side here, or remove minus I1 minus I4 to the other side here. All of them, all three are the same. Okay. At node number 2, we can do exactly the same thing. We don't know whether the currents I2 and I3 are flowing in or out from the node when you do an actual circuit analysis. So what you do, you give them a reference direction. You say, I'm going to take this one as my reference direction, and then you solve the circuit. If the answer you get is positive, then they are indeed flowing out. If you got an answer you get is negative, then the current is actually flowing in the opposite direction. So here let's apply the first statement. Sum of all currents flowing in are equal to 0. I1 is flowing in, I3 is flowing out, I2 is flowing out. So the first equation would be I1 minus I2 minus I3 is equal to 0. Okay, this is the first one. If we say that the sum of all currents leaving the node equal to 0, I2 is leaving the node, I3 is leaving this node, I1 is entering, then the second formulation would be I2 plus I3 minus I1 is equal to 0, which is this one here. Or you can simply say the current flowing in is equal to the currents flowing out. So only one current flowing in, so I1 will be equal to I3 plus I2, which is the last formulation. All three are identical. Okay, but it's just a different way of looking at KCL at the node. So where does KCL come from? Actually, KCL comes from electromagnetics. There is something called the conservation of charge. You say if you build a certain closed service like this one, there is some charge inside. If this charge starts to leave the service, then it's causing current. But when this current takes place, then the charge inside is going to be decreasing. And this is what this law is saying. This is simply saying this is a current flowing out. You usually multiply the current density by the area, but in the general case, it becomes something called the surface integral. You're going to hear more about this in electromagnetics courses. but this is the rate of change of the charge inside. We know that the current is the rate of change of the charge. This negative sign is saying if there is a positive current flowing out, then the charge inside is decreasing, which makes sense, because when there is a positive current means that positive charges are leaving, and then the charge inside that volume is decreasing. Now, if d by dt, if this term does not change that much, we are at steady state or very low frequency, the time derivative of this one is very close to zero. We usually, ideally, it's equal to zero, okay, at very low frequencies. So this term becomes zero. It's very low frequency, and this will give you then, if you build any closed service, or you build like we have in the node, we have this node here, for example, okay. If you surround it by a circle, then all the currents leaving that circle must be equal to zero. And this, what this equation is saying, in 3D becomes a sphere. The sum of all currents leaving a sphere will be equal to zero. And this is what you have here. If you build a very tiny circle around the node, this is what this is saying. So what I'm trying to tell you here is that at a very high frequency, Kirchhoff current law does not hold. Okay? The book may not say this at this stage, but Maxwell's equations are the most general, and they apply to a very high frequencies in the optical frequency, so light hundreds of terahertz. But for low frequencies, few megahertz, a few kilohertz, and so on, KCL is okay. It's fine. We can use it. We work with it. It helps us makes our life easier in analyzing circuits. Okay, but just keep in mind, KCL has limitations, and it originated from electromagnetics. Okay, we have this nice circuit. This is part of a bigger circuit. There's a bigger circuit. I'm not showing it to you. We have here a number of resistors. I forgot to write this one here. This one is also 1 kilo ohm. The value does not really matter in this case. We have 4 ampere flowing out here from this branch, 2 ampere flowing into this branch. There is a current I flowing out. There is a current minus 3 ampere flowing in. When I say minus 3 ampere this way, I mean that there is 3 ampere flowing in the opposite direction. Okay. Now I would like to determine I using this given information, using KCL. This is my target here in this question. Of course, I can, what I'm going to be doing here, I would like to get the value of I. So there are 2 approaches. The first one is a brute force application of KCL. What I'm going to be doing here, I don't know what's the current flow here, so I'm going to define a current here. I'm going to define a current here, and I will assume they flow in this direction. I will define a current here, and I will define a current here, and I will give them this direction. I don't know their actual values. Okay, I'm going to give them this direction, this reference direction. If their values turned out to be positive, great, then they're flowing in the assumed direction. If their values turn out to be negative, then they are flowing in the opposite direction. Okay, we'll see. So I will define these, and then I'm gonna go at every node here. This is one node. I will apply KCL. This is one node. I will apply KCL. This is one node. I will apply KCL. This one node. I will apply KCL. And then I will try through manipulating these 4 equations to find the value of I. Okay, this is my plan to solve this question. But this is a brute force approach. And then I will show you why we can move to a simpler approach in the next slide, another slide. Okay, let's see what we can do. I assume they have a current I1 in this branch flowing this direction, I2 flowing in this direction, I3 flowing in this direction, I4 flowing in this direction. Now let's apply KCL. Here, the current flowing in is equal to 2 currents flowing out. So minus 3 is equal to I1 plus I2. Okay, at this node, we have 1 current flowing out, 1 current flowing in, another current flowing out. So I can simply say that I1, which is the only current flowing in, is equal to 4 plus I3. Or if I reorganize it to move the constant to the other side, I get this expression. 4 is equal to I1 minus I3. So I1, the current flowing in, is equal to the sum of the 2 currents flowing out. This is one way of writing KCL. So I1 is equal to 4 plus I3. I end up with this equation. Let's go to this one here. Okay, so I have 1 current flowing in, a second current flowing in, 1 current flowing out. So I can simply say that I4, which is the current flowing out, is equal to I2 plus 2 ampere. The only current flowing out is equal to sum of the two currents flowing in. So I4 is equal to I2 plus 2. If I reorganize it, I can put it this way. Okay, and then the last equation, which and this is why I selected the direction of I3 and the I4 this way, because these two currents, they are summed at this node to give us I. So I, which is the only current flowing out, is equal to the sum of the two currents flowing in. I is equal to I3 plus I4. Take a look at all these four equations. I needed only do one trick. I summed 2 and 3, and the sum of 2 and 3 is good. Why? Because if I sum 2 and 3, I get I1 plus I2. But I1 plus I2 is known. It is minus 3 ampere. So I can get rid of minus 3 ampere. And then when I sum them, I get also I3 and I4. But I3 plus I4 will give me I. So here this becomes 2 is equal to minus 3 minus I, or that I is equal to minus 5 ampere. Of course, the circuit looks scary in the beginning, but when you write the equations and you manipulate them to get rid of I3 and I4 and regenerate I, we were able to solve for I, and I is equal to minus 5 ampere. This is a brute force approximation, and it may not be very clear how to simplify that in some application. There is another easier way of doing this. I'm going to show it in the next slide. The easier way is to take back KCL to its origin. KCL is simply saying build any closed circle and the sum of all currents entering that circle is equal to 0. So what I'm going to be doing, I'm going to build a circle that encloses my circuit, and then I say the sum of all currents entering this node are 0. This is the origin of KCL. We call this a super node. Why is a super node? Because you can have many components inside it. So what is this saying? I have how many currents flowing in? 1, 2 flowing in. I have how many currents flowing out from the super node? I have 1 and 2. So I can simply say minus 3 plus 2 is going to be equal to 4 plus I. If you simplify this equation, you get I is equal to minus 5 in just one equation. Okay, so this is the concept of a supernode. It originates again from Maxwell's equations, because KCL originated from Maxwell's equations from the continuity of a charge equation. Okay, the second law, the second important law for us is called KVL. KVL it can again be applied in 3 different ways. They are all identical. They give you a difference of a negative sign, or you can move some of the terms the other side, but they all give you the same equation. The first one tells you, okay, you go around a loop, any loop, in the clockwise direction, and you sum the voltages, you must get 0. Or the second expression, if you go around the loop in the counterclockwise direction, and you sum all the voltages, you must get 0. And the second one is saying, if you pick any 2 points, and then you sum the voltages in the clockwise direction, must be equal to the algebraic sum of the in the counterclockwise direction. These 3 are actually identical. They are the same thing. And the most important thing when you apply KVL is to know how to put the proper sign for the voltage drops. This is where most students make mistakes. Okay, so let's proceed our discussion of KVL. And again, as I said, the most important thing is to put the proper signs for all voltages. Let's have this simple example. This example has a voltage controlled voltage source. So the voltage between here and here is 4Vx, and the controlling voltage Vx is the drop across this resistor. This is a voltage controlled voltage source. We have to write KVL using three different approaches. First, let's go in the clockwise direction. When you go in the clockwise direction, when you move from negative to positive, you include the drop as a positive quantity. When you go from positive to negative, you include this negative quantity. So let's go around. Let's move in the clockwise direction. I'm going from negative to positive. This is going to be 4Vx. Plus, I'm going from negative to positive plus Vy. From negative to positive plus Vx. From positive to negative minus 12 is equal to 0. So this is this first equation here. Okay, so this is KVL in the clockwise direction. For Vx, I'm going from negative to positive in the clockwise direction, okay? This is negative to positive for Vx, negative to positive plus Vy, negative to positive plus Vx, from positive to negative, then minus 12 here. Let's go in the counterclockwise direction. In the counterclockwise direction, every time I'm going to move, I encounter a drop from negative to positive, I'm going to count as positive. So let's go this way. This is negative to positive, then we have plus 12. Positive to negative minus Vx. Positive to negative minus Vy. Positive to negative minus 4Vx is equal to 0. So you can see 12 became now positive because I'm moving from negative to positive, while Vx became negative drop because I'm going from positive to negative in the counterclockwise direction. So you can see that this equation and this equation are identical. The only difference between them is a negative sign. And when you solve a system of equations, having a negative sign does not affect the solution, as you studied in your algebra courses. Now, another way which I found more convenient is simply say the voltage supplied by the source is equal to drops across all other components. So you can see, I can simply say here, this is 12, from here to here is 12. So I'm now considering this point here and this point here. So from here to here in the counterclockwise direction, I see plus 12. Okay? While I see here these drops are Vx, Vy, and 4Vx. So I'm going again here in the clockwise direction. So I went counterclockwise from here to here. I'm going clockwise from here to here. So here this will give me 12 equal to 4Vx plus Vy plus Vx. Okay, and this is the last equation. So you can see I picked these two nodes. I want to restate this again. I picked these two nodes. Okay, this one and this one. I moved here in the counterclockwise direction, and I moved here in the clockwise direction. And I'm gonna say that this voltage must be equal to this one. And again, this equation here is identical to this one. Identical to this one. Only difference is that I moved 12 to the right hand side here, and I moved these three terms to the right hand side in the second equation. All three equations are the same. They are saying the same information. Okay, so where does KVL comes from? It actually came from electromagnetics as well. It's the voltage drop is the work done by the electric field. Work done means you multiply the electric field by distance. In general, this becomes, for an arbitrary contour, this becomes something called line integral. You don't have to worry about the meaning of line integral for now. But this is a voltage drop between A and B. It is the work done by the electric field to move a charge against the electric field from point A to B. Okay, so here you have this. This is very famous law of electromagnetics called Faraday's law. It is simply saying that the voltage difference, or the sum of the voltage around a closed contour, is equal to the rate minus the rate of change of the magnetic flux. This is called magnetic flux, and this is called magnetic field. Now, at very low frequencies, this rate of change becomes very little, and this term is effectively equal to 0. And then the equation becomes that the sum of the voltage drop around a closed contour, any closed contour in space, must give you 0, okay? So remember, as the frequency goes higher and the radiation starts to happen, KVL does not hold anymore. And Maxwell's equations will be the most general thing that we have to apply. Okay, so for circuits, low frequency, few kilohertz, few megahertz, everything is okay. We can use this, but as the frequency goes higher and higher, you have to take into account the effect of radiation. Okay, let's consider a number of simple examples. This is a circuit here. We have 3 resistors. We have 1 source. We would like to determine the voltage V1 using KVL. Of course, we can apply KVL in the counterclockwise direction, or the clockwise direction or counterclockwise direction, or we can divide them into sources and so on. For this one, I would say the easiest one is simply say I will go here in the clockwise direction. So this is 12, okay, and for the other ones I will go in the counter. So between these two nodes, this is what I'm going to be doing. I will go from here to here. So I will go this way in the clockwise direction, and I will go this way for the other ones, okay? So I can simply say that 12, this is from negative to positive, so this is 12, is equal to 5 plus 3 plus V1. If I get a positive value V1, then this polarity, this assumed polarity is correct. If I get a negative value, then this assumed polarity is wrong. It is the opposite polarity. Another way of doing it, we can simply go around in the clockwise direction. So negative positive plus 12, positive negative minus V1, positive negative minus 3, positive negative minus 5 is equal to 0. So 12 minus V1 minus 3 minus 5 is equal to 0. It's exactly equivalent. Okay, or I can simply go in the counterclockwise direction. So 5 plus 3 plus V1 minus 12 is equal to 0. Why did I say minus 12? Because when I move this way, I encounter positive to negative change. Okay, all of them are exactly the same. We're simply summing the voltage drops in one direction. So I solved this problem using all three approaches. Clockwise direction, 12 minus V1 minus 3 minus 5 is equal to 0. You get V1 is equal to 4. Counterclockwise direction, 5 plus 3 plus V1 minus 12 is equal to 0, which also give you V1 is equal to 4. This equation is the negative of this equation. The solution will still be the same. Or you can simply say the supply voltage is equal to the sum of the three drops. In that case, what you are doing, you are moving clockwise from here to here between these 2 points, okay, and you are going counterclockwise from here to here between these 2 points. So you can simply say that 12 negative to positive is equal to 5 plus 3 plus V1, which is the last one, will give you exactly the same answer. Okay, so it's very important to understand KVL can be applied in many different forms. Three forms in specific. Okay, this question, I like this question a lot because it helps you to understand how to calculate the voltage difference between any 2 points in an electric circuit. Here we have two sources. One of them is a constant voltage source, 12 volts. This one is a voltage controlled voltage source. So the voltage between here and here is equal to 4Vx, where Vx is the voltage across this resistance. And you want us to use KVL to find VDA, the voltage between point D and point A, and VBE, the voltage between point B and point E. Okay, what we'll have to do here when you say VDA, I'm gonna use actually it's simpler to calculate VAD, and I'll show you why. The point E is higher in potential than point D by 1 volt. Why? Because you can see between point D and point A we have only one resistor. It has a voltage drop of 1 volt. So if this one was 4 volts, okay, so this one is gonna be 1 volt higher. So point E will be at 5 volts. Now point A is higher than point E by 4Vx. This is all coming from KVL, from applying KVL. Okay, so so I can see if this is higher than this one by 1 volt, and this one is higher than this one by 4Vx, which is equal to 8 in this case, then point A is higher than point D in voltage by 9 volts. So I can simply say that VAD is equal to 9. Okay, so it's very important to understand when you move from one point to another, there is either voltage drop or voltage gain. And you can simply say from this symbol one here that the voltage at point E is equal to the voltage at point D plus 1 volts because of this polarity. Okay, so I can simply say that VAD is equal to 1 volts because VAD is how much VE is higher than VD, and this 1 volt here in this case. VAE, which is the voltage difference between A and E, is equal to 8 volts, 4 multiplying 2. So if this one is higher than this one by 8, but this one is higher than this one by 1, then point A is higher than point D by 9 volts. Okay? The same thing will do it for between point B and E. A is higher than E by 8, B is higher than A by 1 volt because of this drop, because VBA is equal to 1 volt. So I can simply say that VBE is equal to 1 plus 8. And what you can do, you can imagine that I am actually, one way of doing it, imagine that I'm going in the counterclockwise this way, and going in the clockwise this way. And going the clockwise this way is going to give me VBE. Okay, so here this will give me VBE, while this one will give me VBE through the different, another way, summing these drops, these two drops. Okay, so to summarize, I want to get, I want to get VDA, but I will get instead VAD and multiply it with a negative sign. VAD is 1, so point E is higher in voltage than point D by 1 volt. VEE is 9. Point E is higher than point E by 8 volts. Then I would like to calculate the voltage difference between point A, which is here, and point D, which is here. Okay, so what I will do, I will go in this direction. Okay, I'm going to go in this direction to calculate VAD. So VAD, you can see when you go around, you have 1 plus 8. Okay, then VAD is 1 plus 8 is going to be equal to 9 volts. But I'm looking for VDA. If point A is higher in voltage than point D by 9 volts, then point D is lower than point A by 9 volts. Then VDA is equal to minus 9. The same thing, you do it through VBE. For VBE, you can simply say that VBE, I want to get the voltage difference between here and here. I can simply go in the same direction here, in the clockwise direction. So I'm going to see first voltage gain of 8 volts, and then another voltage gain of 1 volt. Then VBE is going to be equal to 9 volts as well. So this is 9, and VAD is also 9. Is there another way of doing it? Of course there's another way of doing it. For example, I could take the hard way. I can go all the way around between B and A this way. Okay, so I can do it all the way here. So I want to calculate VBE. So I have to move from E to B. You can see I'll show an alternative way. So if I move from here to here, let's see. So this will give me, let me see here. So this will give me here, okay, let's see. You get here one volt, okay. This one here is 12, okay. Actually, yeah, so this is fine. So this is calculated as -1 because you go from positive to negative. This one is calculated as plus 12. You're going from negative to positive. Then the sum of these two is equal to 11. And this is going from positive to negative, so it's going to be calculated as -2. So 11 minus 2 is equal to 9. So this is correct. Yeah, I started, when I looked at this one, I saw it was an opposite polarity. So when you go, I want to calculate VBE. I went in the first case from here to here. In the second case, I will go from here to here. This is a way longer route to calculating it. So in going from here to here, I encounter three drops. This one is negative because I'm going from positive to negative. This one is positive, I'm going from negative to positive. And this one is negative, I'm going from positive to negative, okay? So VBE still is equal to -1 plus 12 minus 2, so it's equal to 9 as well. You can do exactly the same for VAD. You don't have to calculate it through this branch. You can calculate it from here to here, and I will leave it for you to do that. You go from this point to this point, and you sum the drops, and you'll see that VAD is indeed equal to 9 volts.